covered these books like Fundamental of Aerospace Navigation and Guidance. Another is Modern Navigation, Guidance and Control, and Tactical Strategic Missile Guidance. Okay, where we will study about the homing missile and ballistic missile, optimal guidance. Okay, so all we will study some about in this book, and some parameters in this book. So why we are studying this subject? The main objective is to describe the fundamentals of guidance, navigation and control, and then illustrate the design and analysis of GMC processing. So this is the same midterm is 30 marks and the final exam is 40 marks. Then you have some activity assignment which has 20 marks. So I designed the course outline like this. Week 1 and 2 you already know very well from your earlier education, like deterministic system theory, numerical techniques. So week 1 we will study about introduction to system and control theory, application, linear dynamic system. Again, you are very well know about the linear dynamic system, LTI system, linear time invariant system, controllability and observability. And because we apply the guidance navigation algorithm to the deterministic systems like LTI system. So first we memorize what is LTI system, what is controllability, what is observability, because our system, all systems are a linear time invariant system. So we apply estimation and tracking algorithm to the linear time invariant system. And then of course these are very useful mathematical techniques that we will apply. So you are already very well know about Laplace transform, differential equation, and again Z transform and difference equation. So now up to this, the week number 3 and 4 are very interesting part. The guidance navigation control processing. Here we describe the linear, non-linear intercept of GNC, target signal processing, GNC system, analysis and design, and target tracking state modeling. Okay, here target means the vehicle. Target means a vehicle because we are going to design the guidance and navigation system for the vehicle. Okay, so here vehicle state modeling. Okay, and then after modeling and designing the system, we apply some filtering and estimation technique. Okay, where we will study nonlinear filtering like gamma filter and prediction and other filter design performance. We will check everything. Then week number 5 the homing loop, and week number 6 method of adjoints, and here adjoint of what is the adjoint of how we make the adjoint of deterministic system and closed form solution, navigation, position fixing system, position fixing, navigation and system order design relationship. Okay, here just we only introduce and try to understand how we perform navigation, how we calculate the velocity, how we calculate the altitude, and how we calculate the position fixing, and what are design requirements for the system. Then we will have a mid exam. Then we will go in deep the initial navigation. So we will study two types. First one, initially stabilized initial navigation. This is we call ISIN system, and then step-down inertial navigation system. Okay. Then there are many guidance law. This is a complete chapter. So we will study guidance law. Then we have to apply the guidance law for the homing guidance and the ballistic guidance. There are other guidance techniques like optimal guidance and static guidance, but we will study just about the simple technique, homing and ballistic guidance. Then the navigation guidance filter design. Okay, there we studied target state estimation, practical navigation and guidance filter design. And then week number 14, we will study about the radar tracking and advanced navigation system design. And at the last, this is just introduction to flight control system design. Okay, so and finally we will have a final exam. So how about it? Very interesting subject.
Yeah, interesting.
All chapters are very useful for your research and for your career. Very important. Okay. So today, just we will study as an introductory part, introduction and what is problem statement and simple system and control theories and application. Where we will know why we are studying this subject. This is very widely used subject and very good research area. So here we understand why this subject is important. So why we do guidance? Guidance is concerned with the questions like what maneuvers should we perform to cause the vehicle to go where we want. Here we actually describe the vehicle reference trajectory. We want to guide the vehicle that this is your path. We actually design a path planning. We design a path planning so that the vehicle will go through that only this path. Okay, so we want to perform to cause the vehicle to go where we want while meeting some design specification. Navigation is concerned with the estimation. Once we have made the path planning for the vehicle, then we have to check through the navigation, through the estimation, where we apply some estimation algorithm to check where is the vehicle, what is the velocity, what are its angular orientation and angular rates. Okay. Here we apply the estimation algorithm. Okay, and then control is concerned with the questions like how we control altitude, time of arrival and departure, and trajectory tracking and navigation control. Okay, because sometimes and while guidance in path planning, many object could come. Many object comes in front of the vehicle, so vehicle can collide. The vehicle sometimes crash because many objects surrounding the vehicle. So we want to control so that the vehicle cannot collide to any other object. Okay. So what is problem statement? We consider three basic vectors. Each vector contains the variables like this, which specify the position, angular orientation of the vehicle and their time derivative, means the velocity, position, velocity and orientation with respect to the different reference frame. So x of t denotes the actual state of the vector of the vehicle. This is the x of t is the actual state vector of the vehicle, and x r of t denotes the reference state vector of the vehicle. That some reference trajectory we design, we want to make a desired reference trajectory that vehicle should follow, and this is the estimated state vector x and have a cap that denotes the estimated state vector. That is the value of the state. That is the value of the state vector is estimated by the navigator based on the sensor measurements. So here navigation use the sensor measurements like radar to calculate the estimated position of the vehicle. So using the above variables, we can define some guidance and navigation error. So above the vector follow this equation and this equation, because we have in the problem the guidance error and the navigation error. So what is the guidance error? The difference between the x of t and the reference trajectory. This is actual vehicle state vector and the reference state vector, and this is vehicle state vector and the estimated state vector. So why these error comes? The guidance error is the difference between the where the vehicle is located and where it is supposed to be. So it generally caused by the disturbance acting on the vehicle, such as wind, gust, currents and thrust misalignment. Okay, suppose we have designed up some path planning, some path we have already guide the vehicle that you have to go like this way, this way, this way, this way. Okay, we have already mentioned, but sometimes due to this errors, wind, gust, currents and thrusting misalignment, the vehicle can suppose to can move to other side. Okay, so here, so what is error? The difference between the vehicle is located and where it's supposed to be. So sometimes what we have designed the path, the vehicle go to other side. Okay? And the navigation error is actually the estimation error. Okay, it's the difference between the where the vehicle is located and where the navigator believes it is. This is actually the estimation error. So, and this error is generally due to the uncertainties of the sensor measurements. So sensor measurements have many uncertain measurements because of many collectors. Okay? Because the sensor receives the measurement from each and every object, even the wind. The sensor, the radar can capture the wind measurements as well, because sometimes the wind has some many particles. So each particle generates the measurements, and the wind is also the source of creating the measurements. So in these uncertain measurements, the navigation error or estimation error occur. Now if we combine the navigation and guidance in broad terms, it can be stated that causing the vehicle to follow its desired path despite disturbance and navigation uncertainties. Disturbance means the wind, thrust misalignment and other things. Uncertainties means the measurement, the radar measurements or sonar measurements. So we want to vehicle to follow its desired path. In other words, we want to go where we are supposed to go, despite the fact that we don't know exactly where we are and that our motion is undergoing unpredictable disturbance. So suppose, assume that we guide the vehicle based on navigation. So that is, we take the guidance decision assuming that our estimate x of t is indeed x of our estimate of x of t is indeed x of t. It means the we are supposing that the x of t is actually the estimate of x of t. Okay. means in the we assume that x of t is itself a estimated value of x of t. Okay, we are considering the ideal case. Ideal case in this case, ideal case we are considering that x of t is itself a estimation. Okay, so that is we take the guided decision assuming that our estimate of x of t is indeed x of t itself. This result in estimated guidance error like this one. So we replace x of t with this variable and minus the reference trajectory, that is the difference between where we believe we are and where we are supposed to be. Now we set some error bound. We have a bound on the estimated guidance error, that is we have found a positive number epsilon g, this is error, such that the estimated guidance error is less than epsilon g or equal to epsilon g. Okay? And also assume that we have a bound on the navigation error, that is we have a positive number epsilon n, such that the navigation error is less than or equal to epsilon n. Now we have to combine. We combine both navigation and guidance error, because the navigation and you want to combine both system together, because the system can be combined using both capabilities, navigation and the guidance. Then a simple application of triangle inequality yields this equation. Here the first part is the estimated, it is a guidance, it is a navigation error. First part is navigation error and other part is the estimated guidance error. Okay, first part is navigation error and other part is the estimated guidance error. So if we solve this equation will become like this one, because we separate this equation. The mod is a whole equation. We want to separate this one like this one, separate. Okay. Now this is equals to the epsilon n navigation error, and this is equals to the estimated guidance error. So overall, our equation like this one will becomes the estimated guidance and navigation error, like this one, estimated guidance and navigation error. So our guidance error should be less than or equal to the sum of the navigation error and the guidance error. Okay. So in equation number 1 implies that we can guarantee a bound on the true guidance error. In other words, the small navigation error and small estimated guidance error imply a good guidance. Okay. Therefore, in practice, we proceed as follows. First, we develop the navigation strategies. It means we first apply some estimation algorithm. First, we develop the navigation strategies and quantify their errors. Then we obtain a guidance law and analyze their performance in absence of navigation error. Okay. So therefore, in this book, we will first study about the navigation, then apply the guidance. Okay. So this is the basic strategies. First, we develop the navigation strategies, so that our navigation error become very small. Then we will apply the guidance law. And we will assess the degradation of the performance of the Guyon's law due to the navigation error. Finally, we will study and design and analysis of the GNC processing. Okay? Is that clear? Shall I speak slow? Or okay?
Okay.
It's okay?
Yeah.
Again, you are very well know the basic system, what is system, and we are studying some very simple example. So today's lecture is very simple. So a system is simply a portion of the universe or a system where we postulate that some signal cause the other signal, means cause and effect. The system is the cause and effect properties. The cause and effect. This input is cause and effect. Cause and effect relationship of the system is called the system. So such as a cause signal input and the effect signal output. Okay, here we represent their cause effect relationship in the block diagram system. Suppose we apply some force to the system like this one, then what is the effect of the in the output? Effect of the some displacement or some velocity. Okay, so cause and effect relationship. So for example, in this example, in a spring system, we typically postulate the force is the input and the deformation is the output, like displacement. Now we will study system characterization, like linear versus non-linear, and like causal and non-causal system, and so on. So linear system, the superposition principle holds, such as linear combination of input produces the output as the same linear combination of respective individual outputs, like this one. So sum of output is equal to linear combination of individual inputs. Okay. Otherwise, the system is called the non-linear. For instance, a spring system is often modeled as linear. Okay. And static versus dynamic. In a static or memoryless system, there is sometimes we call the open loop, because no memory, it goes straight forward, and dynamic is have a memory. So sometimes we call it the feedback, because it has a past values, but it does not have a past value. The static, the output at any time depends only on the input at the same time, but does not depend on the past time history, like this one. Suppose tau is some past time, tau is some less than time t. So otherwise the system is dynamic. So dynamic system have some past values as well, and also it knows the current and past values. So typically the mathematical description of a static system is in terms of algebraic equation, whereas that of dynamic system is in terms of differential equation. Okay. And for instance, the string of figure number 2 is static, where a mass string such as figure number 3 is dynamic. Okay. Why the previous one is static and why this is dynamic? There is just difference of the string. There difference of mass. This is string. This is a static system, and this is the if we put some mass, then this is the dynamic system. So why? What is the difference between the figure number 2 and figure 3? This is very basic example. Basic example. the figure number 2 where you cannot see any mass, just spring. Okay, and the figure number 2, this is a static system, and it does not have a, it depends on the current output only, not the previous past time history. So this is static, and this one is a dynamic. Okay, where it has it depends on the input at the same time as well as the past time history input. The dynamic system depends the same time input as well as the past time history input, but the static depend only on the input at the same time.
I'm a little confused with what's mean of that gray square on the screen. Gray square.
Great.
Yeah. What's mean of that gray square? Oh, figure 3.
Here is great.
That gray square on the screen. That is great.
Yeah, bricks, mass.
This.
Yeah. So due to its mass, it becomes a dynamic because now this system depends on at the same time and as well as the previous past time history, because when we push here, when we force upward here, so then we can note the each input value, like this one. Here we push here, then it will go do not go backward, because we are still have a force inside this one and also the friction force. Then at this time, what how much the displacement cover the one output, and then we force another time, we pull another time, then at this time how much the distance covered, then we again pull other this time, then at this input the force here F1 and here F2 and here F3, we apply 3 input F1, F2, F3, and then displacement is the output like X. So here suppose X1, then if we pull the mass over here, then X2 and F2, then we pull far away like this one, then F3 and X3, and then if we release, then it will go back using the same value X3, X2, X1. Okay?
Can you show figure 2?
Figure 2 is just spring.
So I think the mass make a memory, because static is memories and dynamic is memory. So mass makes the memory.
Yes. Now the time invariant versus time varying. So time invariant system and orbital time shift of the input produces exactly the same time shift of the output. Okay, suppose t minus tau is the time shifted in the input. Okay, then output should be shifted by the same time. Okay, if we apply time shifted minus tau time, then output should have shifted the minus tau time as well. Then this is the time invariant system. Okay.
Yes.
Otherwise, time varying system. If we apply the shift minus tau time, but output does not have minus tau times vary, then this is called a time varying system. Okay. So, in other words, The delta tau represents the time shift of the input, this one. Then for invariant system, for all signals u and the time magnitude, we have this one. We have a function of this one. The shift in time the same as the shift in output. Otherwise, the time varying. For example, the spring in figure number 2, where the spring stiffness is constant, is a time invariant system. Causal and versus anticipatory. In case of dynamic, a causal system y of t is determined by u of p, tau less than time, where time response, in the time response the tau is less than or equal to time, but does not depend on the u of t greater than time. Means if we draw some coordinate, x coordinate, then the causal system only those output values which have a time response less than time t. But if the other side, if you go far away from the time t, then it is not the causal system. Okay, like this one. This is causal system. And this is not. Okay. Here tau is some like this. This is time. This is causal system. But if the output will increase over this side, then this is a non-causal. And otherwise system non-causal or anti-sectarian. For instance, the mass spring of figure number 3 is a strictly causal system. Why? Because it depends only on the present and past input values. The figure number 3, as we discussed, due to mass, it possesses a memory. So dynamic system. So it depends only on the present time and the past time values. So the figure number 3, which have a spring and the mass, the system is causal and dynamic system. And then lump parameter versus distributed parameter. In lump parameter, the mathematical description is in terms of finite number of ordinary differential equations. Whereas this distributed parameter system, it is in terms of the infinite number of ordinary differential equation or partial differential equation. So, for example, the mass spring system of figure number 3 is lump parameter. Okay. Our system that we will study is the lump parameter. Okay. We apply the ordinary differential equation because our system, the guidance system, have a lump parameter system. Okay, like this one. So our system is dynamic, so we apply the lump parameter. Now deterministic and stochastic. In the stochastic system, some signals are random process. That is, they are unpredictable, but exhibit statistical regularity. Okay. Otherwise, the system is deterministic. For instance, an aircraft flying through stochastic turbulence in the stochastic system. Okay. So we will study the guidance navigation. Is this stochastic or deterministic? What is the guidance navigation? It is stochastic or stochastic? Yeah, good. Stochastic, because they are unpredictable to determine the position and velocity. So in view of the preceding lectures, the system considered in this GNC course are mostly linear, dynamic, time varying, strictly causal, lump parameter, and stochastic. And this is the class of system that is the most relevant to the study of navigation and guidance. Here time invariant. Here is mistake. Here mistake time invariant. Our GNC system is linear, dynamic, time invariant, and time invariant, causal, lump parameter, and stochastic.
So, Professor, many systems have a time varying system or many time varying systems. So we don't apply the time varying system, the GNC technique.
Yes. This is also possible. Sometimes we have a varying system. Yeah, but at this time we apply the linear and dynamic system. We consider the linear dynamic system to make sure the output is linear to the input, and output also is dynamic, and it has a past value, so we can describe the effect on each input. Okay, so we can analyze the system, what is the output to each of the input. So the system must have at least a linear, dynamic, and lump parameter stochastic system. So whether it is a time varying or time invariant system, so it is good to be a linear, dynamic, and causal system. Now this is a generic control system where we can see the plant. Okay, this need to be controlled. Controller is unknown and is used to control the plant. Human is exogenous, is not under the authority of the designer. So suppose human is not under your authority, but U2 input is endogenous, is under the authority of the designer. Okay? And Y1 is called performance, and Y2 is the measurement or measured output, is available to the designer for feedback to achieve the performance. So Y2, we can see the result of the performance at the Y1. We can check the result of measured output. What is the measured output? Okay, here we can see the measured output. Here we quantify the performance of the output at the Y1. So Y1 is our hand, is user hand, and Y2 is the designer feedback, like digital multimeter. The digital multimeter have two outputs, Y1 and Y2. So Y2 is the, in this digital multimeter, Y2 is the measured output is the designer specification. And what we are going to check the resistance or capacitance by using the connecting cable is the Y1 output. Okay. The goal of control is then to find a system C or find a controller that causes the signal Y1 to perform well despite uncertainties in the U1. Okay. Remarks that in this book, non-linearities in a dynamic do not play a significant role. Okay, non-linearities in the dynamic do not play a significant role because which we will justify in chapter number 2. Because this book is separate from the literature on non-linear system. Okay, this book is different from the literature on non-linear systems. Okay. So also note that in this book the uncertainties are in the signal rather than the dynamics of the plant. Plant have no uncertainties. Uncertainties always come from the radar or sensor or camera. Okay, plant itself has no uncertainties. Plant like vehicle has no uncertainties. Vehicle can have a misalignment on the thruster. Okay, another problem, heat problem, engine problem, but it do not create uncertain measurement. So this is because owing to sufficient instrumentation, dynamic model of aerospace and defense system are relatively accurate, even though the reading of sensor may be corrupted by noise. Okay, so these systems are relatively accurate, but the reading of sensor may be corrupted by noise. So in that respect, this book is separate from the literature on adaptive control system and model predictive control system. So what is the defense system application? Here we define the path planning, okay, navigation, guidance, altitude control. As we discussed above, that first we will study navigation, then guidance, and then altitude control, because we want to make a small navigation error. Okay, and then guidance. So path planning, the determination of nominal flight path for a vehicle to accomplish a specified objective subject to a specified constraint. This corresponds to choosing the XR, the reference trajectory. We must design the reference trajectory by obtaining the path planning. Navigation. Now estimation of the state of the vehicle from the output of the specified imperfect sensor, and using the principles of geometry and astronomy, this corresponds to computing this one. And guidance, a strategy for following the nominal flight path given the off-nominal condition and despite the disturbance and navigation uncertainties. And finally, the altitude control strategy for maintaining an angular orientation consistent with the guidance law and the constraint despite disturbance. These four areas may overlap. For example, guidance and altitude control interact in the airplane flight, where typically a change of trajectory requires a change of altitude. For example, when to turn aircraft. Sometimes what happens, suddenly the airplane changes the direction or turn around. While turn around, it can be separate from the path planning. It can be separate from the path planning. It is also possible. Or if the airplane turn around, then altitude relative changes. Altitude relative change, because the airplane like this one turn around this. So the altitude relative changes, maybe down, maybe up. So these other four areas may be overlapped in, for example, guidance and altitude control interact with airplane flight, where typically change of trajectory requires a change of altitude. And the instance is that guidance and path planning, which are coupled in homing guidance. When a disturbance influences the pursuer trajectory, rather than returning to the original nominal path. Means what is homing guidance? Homing guidance means something disturbance, means something come across the in the path planning of the airplane. Suppose we have designed a path planning, so the airplane move like this one and this one here, but here some object come across uh, in the airplane. This is unknown object. This is homing guidance. This is the technique of homing guidance. So when this object comes, the airplane automatically moves this one, this way. So sometimes what happens, the guidance of path planning interacts. Basically, we have designed path planning like this one. This is actual path planning. The airplane should have to go this way, but some influence come across here. Then the sensor will observe there are some disturbances or some object, then it should change. So therefore the guidance and path planning overlap. So here the system again design another path planning. So in avoid the crash like this one. So when the disturbance influences the perceived trajectory, rather than returning to the original nominal path, the perceiver plans a new path to achieve the intercept. So this will get, rather than moving the same path, it will create a new path. So let's have some example and line communication and control. Like this one. This is the transoceanic jet linear flight. Okay. This is the control display unit used to control the first flight management system, FMS. This image was taken by the FAA, Instrument Flying Handbook. So what is this control unit? In modern jetliner, the navigation is typically accomplished using the GPS and other electronic aids. Now we are using the GPS system. Path planning and guidance are typically accomplished by specifying a sequence of waypoints over which the aircraft is to fly. Okay. So path planning, navigation, guidance and control are typically integrated through flight management system. So the flight management system have this kind of control unit with an aerodynamic display of use for the pilot, and such as figure number 5. This one, the pilot use this control system for the FMS. In such mission, navigation error may, for instance, that the jet linear over forbidden territory, with a tragic result. So guidance error may, for instance, cause the landing aircraft to overshoot or undershoot the runway, also with tragic result. Means the undesirable result. Okay, undesirable or sudden result because of the navigation error or guidance error. So the pilot will use this control system here. It can navigate and check the navigation error and the guidance error. Okay, so this is the control unit used for path planning, navigation, guidance and control. These all control to be uh, this unit, flight management system unit. And this unit also display the uh, as a waypoints, and they can be used by the pilots. And other system is intelligent surveillance and recognition with the unmanned area vehicle, like this one. Here the pilot can see every object, the navigation map using some radar measurement, and it can like see the navigation. Here is the position of the vehicle, velocity, other things. A large proportion of military unmanned aerial vehicle sorties are tasked with collecting information through intelligence surveillance and recognition missions. This we call the ISR. In this mission, navigation is typically accomplished by combining GPS estimates, NSO navigation system estimates, and radar telemetry. So path planning and guidance are typically accomplished by human remote operator specifying a sequence of waypoints of which UAV is to fly. Okay. First, in the system they always design the waypoints to obtain the path planning. Right? For the path planning, we are required to develop different waypoints to design a path planning. So here the human operator specifies the sequence of waypoints over which UAV is to fly. Because some UAV over the vehicle, this vehicle is running. So some UAV capturing the image and to show the position and velocity and the direction of the car, of the truck, or another object. So path planning, navigation, guidance, and control are typically integrated in the command center with aerodynamic display for remote operators, such as in figure number 6, like this one. Another is intelligence same. In such mission, navigation error may compromise the UAV, especially when combined with the loss of radio link. If it lost the radio link, then navigation error occurs. And of special concern in adversarial situation is the possibility of GPS spoofing. You know, GPS spoofing.
I
You know,
don't know.
yeah, GPS spoofing.
I don't know.
This actually, through a maliciously generated navigation error. Their maliciously navigation error may deliver autonomous UAV to the enemy. Means sometimes, you know, when enemy send a drone to any country, then suppose some drone, this is our land, some drone is some spy coming over here, then we apply GPS spoofing to hack the drone, and safely capture the drone to our hand.
Take the information, the drones.
If some enemy drone is try to attack our land, then we capture the GPS coordinates of the drone, and we hack, and we can command the drone to capture, and then we can call the drone to land over our land.
So some kind of criminal, criminal,
Criminal,
yeah, criminal.
yeah, criminal.
Yeah.
So some criminal attack. So we capture coordinates of the drone to capture the drone in our hand, so we can control the enemy drone. So and this means and the combat battle, when there are many enemies come to our land for a spy or for some attacking with a missile, then we capture the coordinates of the drone or missile, so that the missile should go where we want. So we can command the enemy drone with our reference trajectory by GPS spoofing. Okay, so but sometimes what happens that through non-shields generated navigation error may deliver autonomous UAV to enemy. Why? Because suppose we send some drone to other country, then that enemy can capture our drone because using the enemy can use the GPS spoofing to capture the drone like this one. Yes. Understand?
Yes. Interesting.
So this is very interesting. You can look into the internet. The GPS spoofing means to capture the enemy drone, and the guidance error may also occur and endanger the UAV. So because of the guidance error, the UAV can harm other people. The guidance error, if guidance path loss, then UAV can crash to other area and can damage many people, many humans, can destroy everything. So we want to control. We do not want our UAV, our drone, to lose its path. If it's lost its path due to guidance error, it can crash to other side and it can damage. So and with the navigation error occurs because of radio link, because of the loss of radio link, navigation error occurs. Now homing missile, your homing guidance like this one. This is the homing missile. If some enemy send a missile to our land, then we launch a homing missile. What homing missile do? Homing missile attack that missile which is coming to our land. If we launch a homing missile, then homing missile automatically follow and find the attacking missile. Suppose the missile, other missile is also maneuvering. Other missile, enemy missile is also maneuvering, just like this one here. Then our homing missile is also automatically maneuver and follow the enemy missile and it attack and it damage the missile in the air. So this is used for rescue purpose. The homing missile are capable of intercepting a target despite its maneuver as follows. Whatever the maneuver it occurs, the homing missile actually the use as a rescue. Okay, is used to avoid the enemy target to hit our land. Okay? Some missiles carry a heat seeker. So what is the procedure? So homing missile use the heat seeker. Like this is a heat seeker. Okay, heat seeker. Some missile carry a heat seeker, such as figure number 7, a device that can determine line of sight. Then the heat seeker can be used as a line of sight. Then when we launch the homing missile will follow the line of sight. So that can determine the line of sight from the missile to a heat source, possible exhaust of an enemy aircraft engine. This is actually exhaust or heat seeker. An effective way to guide the homing missile is then to steer it so that its front rate is proportional to the front rate of the line of sight. Then our object is to make the same front rate. Then the homing missile automatically steer so that its front rate proportional to the front rate of the line of sight. Hence, in this situation, navigation consists of estimating the front rate of the line of sight, and guidance consists of steering the missile. So, what we are estimating navigation? Navigation is consisting of estimating the front rate of the line of sight, and guidance consists of steering the missile so that its front rate is proportional to the front rate of the line of sight. This process can be automated through an autopilot such as in figure number 8. Okay, this is figure number 8. Understand?
Yes.
Because it creates some line of sight effect of with the help of the heat engine. Okay. And for homing missile, navigation and guidance error. There are navigation and guidance error may be occur, cause the missile to miss the target. So sometimes due to error, homing missile can miss the target with possible collateral damage. Collateral damage means it can damage to our land. Means if the homing missile miss the target, it will go to other side, because it will hit to some other object or some other land, so it can damage other loss, and also the homing missile is very costly. If the homing missile is damaged in the air, so we lost millions of dollars, because each missile is really very costly. So a homing missile, due to navigation and guidance error, it can damage to some part of the land, or it can be damaged in the air, and both ways we have lost. So the problem is worse when missile autopilot has a sluggish dynamic response. So this is occurred due to the pilot. The pilot which is controlling the homing missile at the ground, because there is an auto missile, there is no, of course, no. So this problem is worse when the sluggish performance of the pilot, because pilot is all responsible. Pilot is responsible to control the homing missile, but if the pilot has a sluggish or is a slow response, sometimes pilot may have a slow manual response, then the homing missile can miss the target. And the spacecraft orbital maneuvers, like this one. This is used for the tracking and data relay satellite system. For spacecraft orbiting Earth, navigation is typically accomplished using the radar telemetry from Earth-based tracking station, like this one. This is the radar-based tracking station. Here we are navigating the spacecraft which are orbiting over the Earth. The outcome of navigation is the orbit determination. That is the computation of the 6 orbital elements of the spacecraft. I mean, this one. This is our Earth. So our spacecraft is first accelerating thrust this way, second and third over this one. So some spacecraft is like satellite, is moving, okay, or some other spacecraft is moving. This the first circle, second circle, and third circle. So the outcome of the navigation is the orbit determination. Okay, orbital determination. That is the computation of 6 orbital elements of the spacecraft. Note that the particular mission of each spacecraft typically puts stringent requirement on its orbit. For example, geosynchronous or sun synchronous means it is moving with respect to the geo or with respect to the sun. It is moving with respect to the earth or with respect to the sun. There is 2 requirement in this mission. So each spacecraft have this kind of orientation. Sun is synchronous or the geosynchronous. So this tracking radar determines the orbital determination where the aircraft is moving and what is the direction of the aircraft is moving over here, and sometimes it moving over the with respect to the sun reference frame and sometimes it will move it to with reference to the earth reference frame. And guidance is typically achieved through the changes of orbit by impulsive burns, as in figure 1.10. Here, this station will check the position of aircraft through the Earth base station. This is Earth base station, like this one. This one. Here we the US space station actually analyzed the where is the aircraft arrived. Okay. So navigation and guidance are typically integrated and monitored in mission control centers, such as in figure number 11. And space mission, both navigation and guidance error may leave the spacecraft on an orbit that is useless for mission at hand. For example, the US sent some aircraft to the Mars planet. Okay, MAR, Mars planet. So when they sent to Mars planet, if they face some navigation and guidance error, so they can miss the aircraft. They cannot see the aircraft because if there are navigation and guidance error, then the spacecraft may be at the orbit. Because if you cannot see the aircraft, then you cannot call the aircraft back to the Earth, because no communication due to the guidance and navigation error. The communication to the spacecraft is lost. For interplanetary travel, navigation is typically accomplished using the measurements of angles between line of sight to bright having object. Radar telemetry from Earth-based tracking station, figure number 12, like this one. This radar track the interplanetary travel. Like yeah, also outcome of navigation is the object determination. Guidance consists of orbit changes by impulse burns, and these activities are integrated in mission control sensor, like the previous one. The final front rate of the interplanetary travel is troubled with significant technical challenges. Here also both navigation and guidance technique may disaster or may have a trouble affect the spacecraft in the mission. Because of guidance and navigation error, the tracking object may lost, okay, may disappear, and may cause a terrible effect the spacecraft and the mission. So this is your homework. Okay, because to understand, because this is our objective in this course. Okay, to understand these problems, we try to find out from the history, from the literature, from the because the U.S. Military faces the same problem. Okay, like to find the documented instance of failure of navigation or guidance in a trans-oceanic jet linear flight. So you have to be specific as to what went wrong and how this affected the mission. So you have to find such example from the literature. These are already happened. And you do not do the whole thing. You have to do only one.
Only one?
Yeah, because I thought we have 4 students, but we have 3 students. So each student have to do this one and find a documented instance of failure of navigation and guidance in a remotely operated UAV. Be specific as to what went wrong and how this affected the mission. And the problem 3, find a documented instance of failure of navigation or guidance in a homing missile. Be specific as to what went wrong and how this affects the mission. And find the documented instance of failure of navigation or guidance in Earth orbital mission or interplanetary mission. Be specific as to what went wrong and how this affects the mission. So you have to be specific this word, what went wrong. Also, first you have to describe what is the mission, then what went wrong and how this affects the mission. So first one is jet linear flight, UAV, homing missile, and this mission. So your choice, what you will choose. One.
Number 1, yeah.
And you?
3.
3. Homing missile, okay, good. And